Okay, so we'll start with a quiz. To prepare for the quiz, close all your notebooks. All the books away. Put all the books away. Of course, this is a homework quiz, but anyway. So this is one of the homework problems. You should recognize it. Okay, listen carefully. This solution.
The greatest common divisor of 33 and 29 is 1. So we can write 1 as a combination of 33 and 29. Now 29 is 4 times 7 plus 1. Here we can get 4 and so on.
It actually goes the other way. You pull the 4 and put down the. Anyway, it's okay.
And then we have this equation. And we can multiply both sides by 2490
Mm-hmm.
to get the equation.
So use this empty space. So everyone follows that he wrote 1 as a linear combination of 29 and 33. That's your first step. Because if you can write as 1 as a combination of that, you can multiply 1 with any number you want, and get that number as a linear combination of 29 and 33. Okay, that's your first step. That one is now is 2. It's 2,490, right? Equals to.
So we have two numbers, but this is negative.
This thing is 2,400. So after you find one as a combination of other ones, you multiply it with 2,490.
So we can add.
No. Okay. So you're saying that 8 times 2,490 is 19,920, and then the other one is 7 times that. So why you have an extra 0? Ah, because you did it with 249. Okay.
And now we can increment this by 29 and decrease this by 33. The equality will still hold. So this should be greater than 0. And this should be greater than 0.
You understand that too, right? Everyone follows it? Because it's 29 times that, if you subtract 33 from the first coefficient and add 29 to the second coefficient, you basically don't change anything. So doing it k times, you're hoping that you can make both of the coefficients positive. That's your aim.
And k equals 603 satisfies the inequalities.
Is it the only one? I see some people found 2 of them.
First found the first one and then did a second substitution. So this is equal to 21 and this is so 21, 57 is the solution. And also we can again increase this by 33 and decrease by 20, 29 and this is another solution.
So from 21 to, you add 33, and then you subtract 29 from the other one. Is this what you found? How many people found this pair? Okay, good. So this is the correct answer. Right? Thank you. You have questions? Any questions you can answer? No? Okay. So this is one of the typical applications of number theory to finding pairs of numbers that satisfy some distribution. Last time I wrote a question on the board, which I said this is one of my final exam questions. Do you want to try that again? Let's do that too. This is another probable example of this. I'm not going to write the whole question, but this is a, listen carefully. We have a 3 by 4 square rectangle. So we have 3 by 4 rectangle with already filled entries 1, 5, 14, 9. And we have these numbers left. So we have 9 other numbers. But there are available 8 spots. And the way we want to put these numbers are so that the sum on each column is equal. And sum on each row is also equal. And they may not be same number. They won't be same numbers. But we want them to be equal. So which of these numbers cannot be put there? and y and 10. How do we know that 10 can't be put there?
We sum all numbers.
Huh? We sum all numbers.
Also, whether it is divisible by 12 or not.
Okay, so all of the numbers, this one too? Okay. So let's sum all the numbers. 1, 5, 14, 9, and then 2, 3, 4, 7, 10, 11, 12, 13, 15. So what's this sum? 6, 20, 29, 31, 34, 38, 45, 55, 66, 78, 78, 78, 91, 106. Okay, so it's 106. And we want to figure out what? This 106 should be like what? So what we get from this 106? So we are saying that all the numbers except one of them goes to here, so it should be divisible by 3 and it should be divisible by 4, right? So 106 minus the number we take out should be divisible by 12, right? Because except that number, everything else goes in there, so it will be divisible by 3 because there are 3 rows, they're equal, and divisible by 4. If something is divisible by 3 and 4 at the same time, it has to be divisible by 12. So what do we get from this? What is the closest multiple of 12 to 106? 96. So if this is 96 and 10 will do. Is there any other number will do this? Is the solution unique? Can you find some other number that if you don't put it there, still works? If you had another number, the difference between this number, 10, this solution, and that solution will be divisible by 12. So the other numbers that could work is like 22, but there's no 22 in the list, or minus 2, but there's no negative numbers. So because of that, 10 is the unique solution. Okay? So 10 is the unique solution. It's the number that if you don't put it, the rest fills it nicely. I asked this in the final, and pretty much half of the class found a way to put these numbers here instead of using number theory. But if you use number theory, it's much faster. Right? Okay, so any questions about number theory, things we have done so far? Anything you want to ask? We actually spend a little bit more time in number theory than usual, partly because I've seen some interest in classroom, and then partly because it's nice to go through this. But I'm going to move out of number theory unless you have any questions. No? Okay, so the new thing you're going to learn is combinatorics. Now, many of you probably seen some combinatorics in high school or maybe even in some courses you have taken. It's common that you see this in probability. But the way we will look at these things a little bit different. We'll look at it part of discrete mathematics, where our focus will be understanding, not using formulas necessarily, but solving problems by using clever techniques. So we'll be approaching combinatorics as an example of problem solving rather than the end results. So we'll not be very interested about formulas that we get at the end. We will be more interested in how we got these formulas. So there will be different philosophy here. So maybe some of you remember combinations, 10 choose trees, and so on. They will be results of the counting arguments we come up with. They will be nice to know formulas for these things. We will derive formulas like this. But our aim is not memorizing these formulas or using them in problems, but rather to understand how you get to these formulas or how you can solve other kind of problems using similar ideas. So it's about philosophy behind these formulas. The philosophy, I mean, what you're going to learn is the way is basically counting. So you learn how to count sets. Okay. So at the end, the problems you come across to will be all different types that none of the formulas, ready formulas, will work, but you have to do something clever to see it as a counting problem and use some counting arguments. So in counting, there are two basic rules or basic ways to count. One way to count is to separate what you want to count into subgroups and then count each group and then add them up. So this is basically called summation rule. You, instead of counting the entire thing, you count parts of it and then sum this up. And this philosophy, this rule, sum rule, comes in many, many problems that you come across. So I want you basically think this rule and as a rule, like we'll have to start with this rule because this is the most fundamental rule. So the rule of sum. Let me write the exact statement and then you'll see I will write also some examples, some questions where this rule of sum coming from. So this is from Grimaldi. If a task can be performed in m ways, while a second task can be performed in n ways, and the two tasks cannot be performed simultaneously, then performing the either tasks can be accomplished in n plus m ways. So the resulting formula is n plus m. I mean, this is a very basic principle. This says it's actually disjoint set, and you're counting two disjoint sets. Assuming that they're finite, the number of elements in disjoint sets, total number, will be sum of the elements in each set. So sometimes you can draw pictures like this. So they have no intersection. Intersection is empty set. Then if you want to know how many elements inside the union, there are this many plus this many. Okay? So if there are 3 apples and then 7 oranges, how many fruits you have? 10 fruits you have. Of course, we don't ask you that way. it comes sort of in a hidden way in many difficult questions. So let me write some questions where this is the principle for counting. So in how many ways, this is one of the questions, can 15 identical candy bars be distributed among 5 children so that the youngest gets 1 or 2 of them. So this is a typical counting problem. You're supposed to know, you're supposed to tell how many ways something can be done. So there's a number of ways of doing something. It's a set of things. All of the ways to do it is an element in this set. And you're trying to count this set. So it's a counting problem. And at this point, you don't know how to count exactly things like how you can distribute things. But this is a typical example to show you can approach with sum rule to separate this into a smaller problem. So the sum rule comes up here by observing that. So solution. So the number of ways to do this. So the number that you're looking for, okay, is equal to number of ways you can do this so that the youngest child gets 1 candy. Okay? So this is the number of ways to distribute so that the youngest gets 1 candy. This is some of the ways to do this, right? With 1 candy plus, so this is a number you calculate with the methods you learn, and then you sum it with the ways to distribute so that the youngest gets 2 candy. It's a very simple observation that the youngest child in this 5 children group cannot get 1 candy and 2 candy at the same time. It's going to get either 1 candy or it's going to get a 2 candy. So either one of these. So there is no intersection of this counting problem. You can't get at the same time 1 and 2. So you can fix one of these numbers, like 1 candy, then 2 candy, and count each of these things, which is much easier counting problem. Because if you have 15 candies, if you already give one of them to youngest one, you're dealing with distribution of 14 candies to 4 children with no restriction. And that's much easier question than the entire question. So you divided your question into smaller questions. This is the principle, okay? So this part we haven't learned it yet, how to do this. So we are not going to continue on this problem. But this is how many of the problems will start. That you will have to observe first you have some sort of sum rule. That you can divide your problem into smaller problems. Again, it can get even more hidden into the problem where this sum rule has to be used. I will write you another question, which doesn't even look like you have 2 cases. How many positive integers n can we form using the digits 3, 4, 4, 5, 5, 6, 7 if we want n to exceed 5 million. So if you want to form a number bigger than 5 million, how many integers you can find like this using these digits 3, 4, 4, 5, 5, 6, 7. So my question is not the entire solution, but how we can see this is sum of two things or three things or sum of some things. How can we apply the sum rule here? Can you tell me if there is any good way of approaching this?
Numbers starting with 5 and 6.
It should start with 5. One of the possibilities is can start with 5.
That's the possibilities starting with 6.
Uh-huh. So the number of digits, number of positive integers and bigger than 5,000, 5 million, is equal to, this sign usually means number of, is equal to number of positive n bigger than, such that the first digit is 5. The first digit is 5. Is 5. Plus, what can it also be? It can be 6, or it could be 7. So if you fix your first digit, it's an easier question to count all the digits, all the numbers you can make. You'll also have no restriction left. There'll be no restriction like it has to be above 5,000. So by fixing first digit, you also guarantee this condition. We also make it easier question for you. Does anybody know number of 7-digit numbers that starts with 6 out of these? Like these numbers, do you know what these are? What's the number of things that starts with 6? 720. Why? So good. Why? Anyway, it's something like 6 factorial divided by 2 factorial, 2 factorial. Maybe it's the right number, but there's a formula for this. So formulas for these are easier. We will develop them in time. But this idea that separating into 5, 6, 7 is something you will have to come up with. There's no formula for this. So what I will do, I will try to teach you these ideas, not the formulas. And formulas are easier to derive. You will find them. But first attack to a problem, to find a clever way to reduce it to another. That's harder thing to do in any math course. So this is what we will be trying to do. Now a little bit subtle, but more interesting, or the more used formula and more used rule, the other rule, is the product rule. So you have actually combination of sum rule and product rule to do many of the counting problems. The product rule is very similar to sum rule. It talks about procedures that can be broken into steps. So if a procedure can be broken down into first and second stages, actually you can do it R stages, but let's write this as a simple way. And if there are m possible outcomes of the first stage, and for each of the outcomes there are n possible outcomes for the second stage, then the total procedure can be carried out in n times m ways. So here it's the product. That's why it's called product rule. You can easily see that this is a slightly different situation. Instead of disjoint union, in this case you're looking at Cartesian product of sets and basically tuples formed by that set. So the total number of things inside a set of tuples is the product of number of elements in each set. A good picture, we'll be drawing these pictures so many times throughout next 3 weeks, is that your procedure has steps. So these steps, it doesn't have to be just 2 steps. You can have more steps. Okay? So this is like first step, second step, and you could actually have more steps. Later we can see that. But suppose that your first step is a procedure, something you do, which can result in m different ways. So there are exactly, say, m different possible outcomes. So this is m outcomes. This is your first outcome of the first. You can think this as an experiment, that you do some first step of your experiment, and you're expecting m different outcomes out of this. And suppose you know that these outcomes are identical in the sense that for each of the outcome, the second step also has exactly equal number of outcomes. This is a very key thing, that most of the counting problems will not have this problem, but will not have this property. But suppose that for each of the outcome, number of outcomes of the second step is also equal to n. So they are equal. This is the key thing. So each of these is n. So obvious thing to observe is that at the end, how many outcomes you will have? It's exact n times m, okay? So at the end, you get n times m outcomes, or m times n outcomes. But we'll have questions at the end of the semester. All you will have to do is draw this picture and multiply these outcomes. And many of you will find it difficult. So it's a very simple principle, but this is the only principle that you could solve even the hardest questions just using this principle. Any of the questions that you will face in this semester about counting is combination of sum and product rules. There's nothing else that you would need to know. Just this rule and that rule. That's important. Also, if you have more steps, of course, this changes. So if you have steps like this is n one different ways and 2 different ways. Suppose you have r steps and r, then total number of outcomes obviously will be product of them. Different ways to do it. Different outcomes. So this is usually called generalized version, but you can see that if you have r steps, easily this generalizes from 2 step to the r step. Let me write a question, then we'll finish with that. Actually, I'm maybe I won't. But like typical things are all combinations. If you know this, like 9 times 8 times 7, like combinations of 10 choose 3. Like these formulas, they're all product rule. So some of you probably seen combination permutation formulas, which involves factorials and so on. Huh? Permutations. That they all involve products. So all these products come from this step, like product rule. So all the permutations, all the combinations, all the counting we do, we'll do it using these 2 basic rules. And some of the questions we solve will not have any formulas. So you'll have to be very clever about how to use these 2 rules. And starting Friday, we'll like write questions, solve different problems using these 2 rules. But these 2 rules you should not forget. They're very important. Okay?